Morning. Yes, just to remind you what we learned previous time, we talked about state space and how to design controller for state space representations of the system. And we described three different methods, which is including comparison of coefficients, Basgura formula, and Ackermann's formula to design that controller for state space. And controller is just a vector of numbers, which is connected to state X. And then you return it back, the dot product kx, you return it back with negative feedback. Okay, so you have that closed loop now, and you multiply the output X by C, you get the performance that you want. Everything is great. You assume also controllability of the state, that you'll be able actually to control each one of the states. Otherwise, you cannot control all of the states. You can control only subset of the state lines. But if you assume controllability, so if the system is controllable, you can move your poles anywhere you want in closed loop, and you can get practically any performance you want based on the location of the poles that you design, right? And zeros, unfortunately, you cannot move this state space feedback. So zeros, they stay in open loop and closed loop. Zeros are the same zeros. So you are not moving zeros at all in state space. Okay, so far. So now we move to another topic, which is called topic of observers. And I mentioned already motivation for that topic, and motivation is pretty simple. Not always you have access to all of the states. So not always you can measure each single state. Sometimes they are computed in some complicated way. Sometimes they are not measurable because you do not have sensors to measure them. And I think this lecture, you might not notice it, but I will tell you that this is one of the most amazing breakthroughs in that entire control theory. There are some development which people developed, actually some theorem, which is extremely unexpected in a way. So it's amazing that this works in general. And to get that work, you need a particular shape of the systems that you're adding to your system to make all kinds of things canceling out magically, and then you get really great solution to problem of observer somehow. So this is actually an amazing solution, but since it's all math, probably you will not even notice it. I will just go like, here's the theorem, let's prove that theorem. The theorem works, great, now let's use it, okay? So it's not that important for the actual use or design of observers, but it's amazing that this is even true. So what I will claim that you actually can connect observer in closed loop without changing anything else. So you're kind of introducing completely new, like imagine that you have regular transfer functions, right? You have block of your plant, then you add in controller in somewhere in the loop, then you can add like feedback controller or whatever controller you want, serial controller, parallel controller, whatever you prefer to have. And then I'm telling you, oh, I will add like huge system somewhere in the loop of that controller, like add-on system. And this will not change anything in the system, okay? Like this part will somehow cancel out in terms of like relations of inputs, outputs, transfer functions in closed loop. You will not see it. It will disappear magically when you're computing all of the transfer functions in closed loop or poles, location, anything, zero location. Nothing will be affected by introducing that huge block into your system. This is the magic of the proposal of that particular observer form. So this was developed for many years. And historically, interestingly, the original observer was developed without even calling that by that name. It was Kalman filter, which was developed in probably 59 or 60, so close to the beginning of 60s, okay? Kalman developed optimal observer. He never probably even thought to design not optimal observer, okay? So not optimal observer was invented 10 years later by Leuenberger. And he is professor at Stanford, still professor at Stanford, emeritus, still professor, okay? And he is known for economics, not even controls or engineering or anything. He is like professor in like economics theory. And he developed all of the observer, and it's called now Leuenberger's observer. But the formula is exactly the same formula that you can find in Kalman's paper, which was like 10 years earlier than that. So it's interesting that people are just reinventing different things when they think about different approaches to the problem. It's very important that you can publish really, really important things, even if you pull it from somewhere else, if you give it a new use or new interpretation. This is important for research that you're doing, okay? So every time you find some new idea or even old ideas that you can apply to some new thing, it becomes a new idea. And many things are like that. Like things like, I don't know, Nyquist theorem for stability is Cauchy theorem, which was invented like 100 years before Nyquist. So it's not a big deal. This is the same theorem, you just apply it to particular purpose in mind, okay? And then it becomes completely new thing, super popular, very cited, very highly cited paper on that, okay? So here is what we are trying to do, okay? This is our unsuccessful attempt number 1 for designing observer. Just to remind you, observer is something which is taking input U, output Y, and tries to guess the state X. So you do not have state X, you cannot have access to that state X, you cannot attach to that because it's like closed plant, right? So you have outputs of the plant, you have inputs of the plant that you give to the plant, right? So you can measure only outputs and you can give particular inputs to the black box, but you do not have access to the internal states of the system. Not always you can measure all of them. So you want to compute them somehow. You want to estimate them. This is called estimation problem. And this estimation problem needs to estimate X. So let's say we have the model. We have matrices A, B, C, D, all of it is known. We know how the system works. We know physics. We know whatever sits in the black box. We developed matrices A, B, C, D. So we have practically linear state space representation. So our observer could be just some algorithm in the computer which is simulating the system and computing access from the same kind of system. And this is our first attempt. So let's say this is simulation and this is real plant. So real plant is black box, you cannot touch it inside. You can measure only outputs of the system and you can deliver some inputs to the system to control it somehow, right? So my first attempt, I know A, B, C, and I ignore D. D equals to 0 in that case, for simplicity. All right? So I run that simulation in my computer, MATLAB, whatever, maybe embedded board, doesn't matter. And then I get that estimated X. Then I multiply that estimated X by C, and I get estimated Y. I don't even need that part because I will just connect controller here, right? So I have access to that X because I simulated it, right? You have access to everything in your simulation because these numbers are running on your embedded board outside of the plant. So you can connect your K here and then return it back here. How was that? What's wrong with that attempt? Why this will not work? This is simple. Assuming that you know well matrices ABC, which is not exactly true, but kind of let's even assume that you know them perfectly well. It still will not work. Why is that? You will not estimate correct access using that.
Why and why not same or better?
You hope, but they will not. You want them to be. I mean, you want the X estimated to be the same as real X, and you want the Y estimated to be as real Y, and using same matrices and same kind of solving of equations, right? So your plant is solving that equation, assuming it's ideal, okay? And your simulation is solving it in parallel with the same input, right? You put in the same input in both of them. So U is the same at every single time point. And you simulating that equation, you're getting some solutions to X. You have the integral solution, right? Explicit solution. So this will be same X. And I'm saying, no, it will not be the same X, it will not be the same Y. Maybe not even close.
You should need to assume that y is y and we're going to get x.
we will get there. But here I'm saying, like, I want to estimate X. I don't even care about that part, okay? I don't care about the specific part. I just showing that this is exactly the same system and simulating technically the same system, right? And then I can estimate that X in the system and I have access to the X, but I don't have access to that X. So I will use that one to control my system, which is theoretically should be the same.
They can be different if, because that is a function that the matrices are same, but the function can be different. So
What function?
the x hat of t.
Why?
What do you mean?
Why it is different? This is what I'm asking. Like, why is it different?
No, I'm saying it can be different.
It can be the same, it can be different. So why can it be different? Like I have same matrix, the same equation, same solution, no? I mean, you have two equations. I'm calling that variable x hat now, okay? Solving exactly the same equation, iterating on the same thing, right? Let's say in discrete case, it's easier to understand. So xk plus 1 equals a xk plus buk, right? And same thing here. Same thing. I'm just calling that x whatever, tilde, hat, whatever. Some other, but the same equation. So next x should be based on these two same matrices, should be the same, right? You have exactly the same equation. I mean, you have two differential equations which are exactly the same. You're just calling the variable different name. Like, why would you get different solutions?
How do you know A or U?
I'm sorry?
Like, how do you know A, or is that estimated?
No, let's say you estimated A somehow from the plans. You have some system to estimate matrices A, B, C, and D, and they are perfect. They are exactly as your original system's matrices. And again, I'm saying this is not true in reality, but for the sake of that question that I'm asking, this is not the only difference, okay? So I have more significant difference here, not only tolerance of like how close your real matrix A to real system A, okay, to your model. Like, there are differences, so it will be a little bit different. But I'm saying it could be not a little bit different, it could be like significantly different. Like the X which is estimated in that system might be like completely different. Not even close. And will never converge to the original X. There is some information missing here in that plot. I mentioned that a few times in that course already. You're missing initial conditions. How would you know your initial conditions of your plant? Like what the x0 is? You don't know it. And you cannot measure it because you don't have access to x. So technically, all you can do with that thing is to choose initial conditions 0. Or whatever else. It could be any initial conditions practically. But if you're solving differential equations starting with initial conditions, you might get completely different solutions from different initial conditions. And they might not even be close to each other, not even remotely close, okay? They could be anything, practically speaking, all right? So this is not working. These two solutions are completely different because you do not know initial conditions of your original system. So here is another attempt, but we have Y. So we can see how different your estimated Y is from your original Y, because Y you can measure, right? And you minimizing that error. So this is what you want. So you want to do something to that thing, to that estimated values of X, such that this error will be minimized. Okay, you want to reduce that error eventually. Okay. And the thing is that you actually can do that. So this is how real observers work. But to do that, you have a million of possibilities here, right? You can modify matrices, you can add something to that equation, you can build some other simulation systems of some kind. It could be linear, non-linear. I mean, all the options are open here. So developing such a formula which will actually work and converge as fast as possible and have all these nice properties of not affecting the controller design at all is almost like a magic that you need just now to come up with an algorithm which is modifying the block somehow without affecting anything in any other computation that will be promised to you to converge, first of all, to the real X. Okay, mathematically, you can show that the estimated X in that system will converge to real X. And also after that, it will be stabilizing the system. And also controller design is independent of that observer design. This is what we will see, all of that we will see today, like how it really works. Any questions so far? But this is where we are going with that. We want to modify that simulation part in such a way that X estimated will converge to real X, and this thing will not affect anything else somehow. So we'll be adding that in the loop, because if you remember, loop will come from here and end up here, which means you just added that entire new thing, adaptable, whatever, with all of the things, okay? And still this like non-existent from the perspective of the controller. Like it doesn't see it at all, right? This is kind of weird, but yes.
When you say observer, do you mean everything outside the blue box in this example, except for human Y?
Mhm. All of that is
Everything else
observed,
is
yes.
observer. Okay.
All of that
So the
part,
error measurer. and
including
the
error
simulation.
measure, including everything. This is observer, yeah. You're taking just U, Y, putting it into observer as two inputs, and the output is X. This is how it works. So, yes.
So is it like a block that is on the backward towards for a backward loop, like feedback on the way of feedback to the input?
This is exactly how it will look like, yes.
Can I ask just?
Yes.
So that error that goes from error to you know, it's the estimated state vector.
Mhm.
There's an an arrow that's going to the blue box, but it's actually not.
It's not-
influencing the blue box. It's
You're
actually
talking about
the
that
X
arrow?
block. Yeah.
It's just changing that block. It's not showing, it's not connected to the blue box.
But it's changing the simulation, right?
It's
It
changing the
makes
simulation
X
block, yes.
hat-
So it's adapting the simulation in such a way that the Y's are coming closer to each other.
Okay.
And then it is promised that also X's will be close to each
Yeah,
other.
'cause it's not influencing the plant at all.
It's not influencing the plant at all. It's all inside. Okay, so this arrow is just kind of variable block. And this is how it will look like. Pretty complex, you see. So this is inside the dotted line, you have that observer circuitry, which is simulating everything. And you can maybe recognize that part, which is, if you remember this implementation of the plant where you have integrators, and this is N integrators, then you have matrix A, and so on. So you have that initial part, which is exactly as your linear system. Okay, so this is that part. But you have also add-on here, and this is that add-on. You have some vector L, which is column vector of n elements, L1, L2, L3, and this is observer's gain that we will need to design to get to performance that we want, okay? So this thing you will design, and this is regular thing from your regular system. So this is CX, and here I'm ignoring D, but you might also have additional D here as usual, okay? So this is for D equals to 0, all right? But you can include D in that thing as well, if you want to, all right? And this is your plant. So what happens is you're measuring Y, you're taking U inside of the observer, so those are two inputs of your new system, okay? And this is your output. So your output will be that estimated X. And here is the equation that we are using, which is very interesting equation actually, with two inputs now. So X estimated dot will be that original simulation as we've seen in the diagram. So this is that thing, right? And now we need to use that difference and multiplying that by gain. So we're taking that error, multiplying that by gain and adding it here to that equation. So this is how it will look like. So it will be that gain L times the difference, which is that error of the output. That's it. This is that simple. Now you can combine it in a different way because you have Y estimated equals to C times X estimated, right? This is by definition. This is that thing. So you can take it inside here and to write that matrix as A minus LC. So this is that L times C, which is sitting here, times X estimated. All right, plus BU, which is from here, plus LY, which is from here. I'm just combining it in a different way. But look what happened here. So if you're thinking about U and Y of the observer as inputs, then you have practically linear system with two inputs, right? And your new A matrix of the observer part will be that matrix. Is it clear what I'm saying? No. Okay. So look, your regular linear state space system looks like X dot equals AX plus BU. Okay. So you want A might be any matrix and B might be any matrix. Okay. Now I can redefine my A and B in different ways. It could be like A tilde, B tilde, whatever it is. Now, if you have multiple outputs or multiple inputs, this will affect the size of the matrix B. Right? So a matrix B might be actually a matrix, not a vector, if you have multiple inputs, right? So here you can combine those two as a single matrix times vector UY. That will be B and L, right? Stuck together, multiplied by U and Y vector. And this might be your new matrix A, which is A minus LC. This is A tilde, if you wish, okay? So it will still have the same form, matrix times vector plus matrix times U, new U, okay? Your new U will have two components, U and Y in that case. But it's still same shape and form of the original linear LTI system, okay, in state space. So you can still manipulate it in the same way. And the convenient part of that is that this connects us to eigenvalues of that particular matrix. Because now these eigenvalues will tell you how fast that observer converges to the solution, which is settling time in a sense of the observer, like how fast you actually will converge to the right axis. So this will give us that information about like how fast you want to converge. More than that, if you remember controller design, we had here A minus BK for closed loop system. Remember that from previous lecture? Now you have A minus LC. This is exactly the same problem, just transpose. Okay, so instead of BK, you have LC. This is the difference technically. So instead of B, you're replacing it with C transpose. Instead of like C, you're replacing it with B transpose, and K you replace with L transpose. And you solve exactly the same problem. So the formulas will look exactly the same, just transposed version, okay, for all the formulas. Same comparison of coefficients, same Basguro formula, same Ackermann formula, just everything inversed because you're transposing all of them. You're replacing, it's like, this is called dual problems, okay? You're just renaming some variables with other names. You're renaming B with C transpose, and you're renaming A with A transpose, you're renaming C with B transpose, and B with C transpose. This is how it works, okay? So just renaming variables. But solution, like the principle of the solution, exactly the same principle. So to design observer, which is to find that vector L, using same techniques that we learned previous time. These are dual problems. And this will always be in that course like that. Everything will be dual. You'll have estimation and controller design problems are dual problems. They will connect all the time in everything you will be doing in that course. All right? Any questions on that part? We will develop all of that in a second mathematically, but it's just, I'm trying to give you a big picture where we are going with that. Yes, so this is implementation of that formula. Yeah.
Right, but the video is on top of the right of LY should.
Nothing is there.
Y had to see it this year. I lost it.
So Y is here. This is Y, this is Y hat.
Oh, Y had is CX, okay.
So CX hat is Y hat.
But Oh, D is 0.
D is 0, yeah.
Okay.
So D here is 0. So I'm not drawing here D at all. Okay, so D in that case is 0. So this is practically implementation of that formula. So you're taking C times X estimated, which is Y estimated, subtracting it from the actual Y, and you get that error, right, which is here, multiplying it by L, you get L times that thing, and you're adding that to your original system, which was without that error, like that, right? This was your original representation of state space. Any other questions so far? Okay, so these are the equations that we have. So X dot, which is sitting inside of that plant, equals AX plus BU. Now, X estimated dot is that thing that you have here. Okay, I'm just copying that same thing. We will be using just these equations to play with it. I want to define new variable, which is X tilde, and this is the error between the states, between the estimated state, which is here, and state which is sitting inside of here. Okay, we will be using that later to prove something which is called separation principle. So I want to define new variable, and we'll be using tilde. In that lecture, we'll be using tilde for that purpose. Okay, this is error, estimation error. This is what I say with tilde. And I have troubles always like in using symbols, because in that course we have too many symbols for all kind of things. You just need to use same symbol for different things sometimes. I will try to avoid it. In that lecture, X tilde is estimation error, okay? And this is the difference between estimated X and real X. And what we want to show that ZX going to ZX, which means that this estimation error goes to 0, converging to 0 as fast as possible. So the transient, which takes the estimated X from any initial conditions to converge to real X, should be as short as possible. So you want like almost in 0 time to converge to whatever you want, right? Okay, so let's see what happens to that X tilde dot. We will write equation for that X tilde dot, like how it is converging, how fast it is converging. And if you remember, if you get to equation of X dot equals AX, so the convergence is dependent on eigenvalues of that matrix A, right? Because it's converging to 0, like A dot X dot equals AX. This is differential equation, matrix differential equation, which is dependent on all the eigenvalues of the matrix A. And if all these eigenvalues are stable and converging very fast, then the sum also converging very fast. All right? This is how it works. Same thing, we are kind of repeating the same trick over and over again and getting to the same linear algebra, basic stuff. Okay, so what that thing is that thing dot minus that thing dot, which is derivative of that thing minus derivative of that thing. And I'm just copying that thing minus that thing, right? This is what it is. So if you do some algebra, BU cancels out because you have BU here and BU there, right? So BU cancels when you're subtracting this one minus this one, right? And then I can open all of the parentheses, and this is what I will get. Okay, so far? But now I can combine it as A here and A there, and you have LC here and LC there. Same coefficient multiplies it, okay? So I can write it like that. And what I have in parentheses here is X tilde back. So I wrote X tilde dot as a function of X tilde. And this is how it looks like. So X tilde dot equals A minus LC X tilde. As simple as that. Everything else canceled out. So what that thing is exactly the kind of matrix that I have here, right? Eigenvalues of that matrix will tell you how fast your observer converges to the real X, or in other words, how fast that vector converges to 0. Because you have just sum of exponents based on the e to the minus eigenvalue, not minus, eigenvalue times t, right? And you have multiple components to add together like that. This homogeneous equation. You do not have any u, any input. So it will all converge to 0 if eigenvalues are stable and fast enough, which means far enough to the left. This is what you want. Now, if they will be too far to the left, this becomes too noisy. So some noise will enter that computation, but in observers, it's not typically big a deal. Why? Because this is just simulation. You do not have any actual noise. You just simulate the system, right? So it's like mathematical computation practically. So here's the formula. So we get to that description of the error change. So this is how error is changing in time, practically based on that equation. From some initial conditions, you might start with any initial conditions. Eventually, it will converge as that sum of exponents based on the eigenvalues of the matrix A minus LC. So we need to design such L that the eigenvalues of A minus LC will converge as fast as we want, which means designing practically location of poles or eigenvalues for that matrix. And we know how to do that because we designed controllers previous time. Exactly the same thing, right? Now, technically, you don't want them to be too fast. And rule of thumb says, again, this is not like theorem or anything. This is rule of thumb. You typically want to choose your observer poles somewhat stronger and like faster than your controller's poles. So if you choose controller poles in particular place, choose the observer poles at least 2 to 5 times to the left from them, faster in a way, okay? So you move them to the left like 2 times, or 5 times, 3 times, or whatever. Not too far away, not like 1 million times, not like a negative 1 million or whatever, but just order of magnitude or half order of magnitude faster, okay? In unit circle, it will mean like getting them closer to 0, all right? This is what it means. Closer to origin, this is faster poles. But for continuous time systems, it's like farther to the left 2 to 5 times, something like that. This is how we design location of observer poles typically. Any questions on that? Yes.
So why do you want to choose something like 2 to 5 times? You want to converge it as soon as possible, as fast as possible, right? So why do you want to even like?
Yes. Yes and no, because what you are doing, you're measuring the real y, okay? In physics, y will be having some tolerance, which means you will not know the actual y. You will know y plus minus some tolerance plus noise, right? This is what you will actually have. So if you will build your state estimator based on incorrect y, and you will do that just based on a few points from y, it will converge to wrong values of x for natural reasons. So the estimator will be wrong all the time. And then you will try to jump fast to a new y, which is also noisy, right? So it will like jump all over the place. These estimators will just change too fast, right? They will converge eventually to, but they will be noisy. They will be jumping all over the place based on immediate y, okay? You want to give it kind of delay, like some time to stabilize a little bit. So this is why you choose it like 2 to 5 times faster, but not like super fast. Otherwise, it will jump to any noise it sees from the output y. Because you, on the input you decide. So you know it precisely, typically. This much better tolerance. But y is what you measure with the sensor from your system, right? So it could be not very exact, yes.
So if your sensor was perfect in principle, it would be best to have the
Yes.
shortest possible.
Right. And this is what actually Kalman filter will do. So if you have extreme knowledge of your output, you will trust it more, right? So it will weight the input-output relations in such a way that it will trust the output and not the model, for example. It will give it a lot of weight in the weighted computation of Kalman filter. That's exactly what the Kalman observer is doing, based on the estimation of noises or tolerances of sensors. Yes. And this is the page, as I promised previous time, you have only one page, and I used on one page to show you one method of controller design. Here I'm showing on one page 3 controller design, 3 observer designs in one page, all of them. Like this is practically the end of the course, okay? Not really. So you have 3 different methods. You have Basgura method, you have Ackermann method, and you have comparison of the coefficients. Here I'm using that in whatever different order for whatever reason, but it doesn't matter. You still have this same 3 methods. So first of all, you're choosing desired location of your observer poles, which are again typically 2 to 5 times to the left. Okay. let's call them SI tilde to differentiate them from the controller poles, which will be just SI eigenvalues, all right? We compute in desired characteristic polynomial as before, and you'll have S minus S1 tilde, S minus S2 tilde, and so on, and you'll get some polynomial with some coefficients which are constants, some kind, okay? Just faster polynomial. Now, method one, you're using Basgura formula. Pay attention that this is practically the same thing, just transposed and order is inversed. Because if you remember, multiplication of matrices transpose is inverse order of each one of them transposed. Okay, and also you're replacing controllability matrices with observability matrices, canonical controller with canonical observer. All of these are dual problems. And if you remember, I even defined canonical observer form as transposes of the matrices from canonical controller form, right? It was like you get A equals to new A equals to A transpose, new B equals to C transpose, new C equals to B transpose, something like that. So I'm just putting these numbers here, and I'm getting observability matrices instead of controllability matrices, canonical observer form, and these are vectors that I just defined here. So these are vectors of these two polynomials, this polynomial and open loop polynomial. Okay, so this is again same thing like in Basgura formulas. Remember, this is not the SI minus A plus BK, it's the original SI minus A determinant coefficients. So the A coefficients are open loop coefficients of your denominator, characteristic polynomial, right? So they are coming here, these coefficients are coming here, then you multiplying, doing transpose on everything, and you get that column vector, right? Now, second method is Ackermann's method, but here you're not multiplying by the last row, you're multiplying by the last column because you have that type of vector, it's transposed vector. From the previous formula, if you remember, it was like 0, 0, 0, 1 row vector, now it's column vector on the other side. And again, instead of controllability, you have observability, and you are replacing with that polynomial instead of the controller polynomial, okay? And you're replacing all of the S or Z with matrix A and getting that matrix polynomial. Any questions on that? So you're just using same thing, same methods, just everything transposed, replaced with different names. And comparison of coefficients, again, same thing. Instead of A minus BK, now you have A minus LC, right? This is the difference. So you're comparing coefficients of that desired polynomial, which is now with tilde, which is a few symbols are different, and you're comparing that to that thing. So instead of BK, I have LC here. This is the difference from the controller design. And then you have all of these coefficients, obviously are functions of L1, L2, L3, and so on. And then you're just comparing coefficients and finding that vector L. Done. This is design. This is exactly the same technique, just a little bit different formulas. Okay, dual problems. Any questions? You look shocked. This is not that bad. Okay. You'll see some examples as well, so relax, you'll be fine. A few years of training, you'll be fine. And this is what we actually want. And this is where magic comes in. Because, okay, now you can estimate the state X, and we know that it will converge to the actual values of X. Estimated X will converge to the values of X based on your design. It will be fast enough, hopefully. And estimated X here will converge to the X which is sitting inside of the blend. Okay, so you can connect it to controller K. But here's the problem. Why that thing even needs to converge in the first place? Because now you are affecting the actual blend with your new signals, right? So you kind of modified U completely based on the estimated X, and your X estimated X at the beginning, not even the real X, it's just starting from some zero initial conditions. and starts maybe just to converge to real x. It's completely different set of numbers, right? It's not even close to your original x0 state when you start the system. So you turn it on, this x equals to 0, this x equals to 1 million, whatever, okay? Like bunch of n numbers, could be any random numbers you want, okay? Some initial state of the plant, whatever it is. So you start and say like, oh, my x hat is converging, okay? But now you're sending wrong signal to that thing, right? Because it's based on estimated wrong vector. You're multiplying it by some values k, which you designed without even thinking about like what happens to the block. And then you're saying, let's return it back, okay? Why it's supposed to work even? This makes no sense. Because now your output y will be changing based on whatever input you provide. And this was not the original intent because your control is not based on the original x. Like who told you that this will even converge to, I'm not saying even to the correct thing, even converge, even stable in the closed loop. Because you're using wrong x from the beginning, you're using wrong x. But it will. This is the magic. Like this loop will work great. More than that, the observer design will be completely independent from the controller design. So controller does not need even to know that you have observer. An observer doesn't need even to know what kind of controller you design to your system. It doesn't matter. The controller will control it from any point that observer provides until it converges, okay? That will take a little bit longer time. Yeah, so you'll have transient response, which is a little bit longer than if you would connect it directly to the x of the plant. So you need to give it a time to converge to the real x. But after that, it will start working magically and it will converge and everything will be great. Okay, this is the magic in all of the theory, why this observer is so wonderful. Okay, so this is what we want to connect. Okay, this is the same thing. I'm just drawing that explicitly, that observer part. Okay, you're connecting that estimated x to the k. And the magic is that previously we connected that k here in the middle somewhere, right? So this vector was coming from here and this block didn't exist at all. And what I'm going to show you, that after I connected the horrible big and complex system, your transfer function from here to there will not change at all. Like all of that will kind of magically disappear somehow when you're connecting like R to Y transfer function. Okay, so all of that will not have any effect on the actual plant or anything like that. Okay, not at all. You will not see it anywhere in the equations, not in the closed loop poles, not in the performance, not in anything. It will just vanish somehow. Magic. So let's see why. All right. And then we'll get to something which is called separation principle. And this principle practically saying whatever I just said. You can design controller and observer separately without mixing them because they are not affecting each other in any way. So let's see why. So here's the circuit, okay? So I'm writing that explicit equations from whatever we see here. It will be a little bit complex, but try to follow the logic here. So U, which is that input, equals R minus KX estimated. So the difference is that previously we had no hat here, right? In the original controller design. Now we have it, so it's different U, not the original U, not the regular loop. Now we have that estimated X coming here, multiplied by K. Second thing, X dot, which is sitting here inside the plant. No, not here. This is X dot hat. But inside X hat is AX plus BU. Now my UU is that thing. So I need to write that thing as a function of X hat, which makes it not possible to combine these two together because X hat is not X, right? In general. I hope that they will converge to each other. So we'll get back to whatever we had before, but they're not. Right? And y equals to cx. Again, I'm assuming that d equals to 0 for that purpose. And this is what I can write about x dot here, because I'm just taking bu plus L times y minus y hat plus ax hat. This is what the x dot is. right? So I'm writing that explicitly. This is what I have. Now, I can practically open parentheses here and to replace y with cx. Is that thing, right? And this is what I will get. I will have ax, blah, blah, blah. This is just algebra. Now I'm just recombining the things together. I'm taking LCX, that LCX outside of the parentheses. Everything else multiplies x hat, right, in closed loop. So now I kind of replaced u with x hat, computed x hat by the observer. So it will be a minus bk minus lc times x hat plus br and lcx. Again, I have both variables x and x hat. And it would be kind of weird to assume that I can ignore one of the x, like practically like, why would that be the case? Because you see the derivative of the estimated x dependent both on x and x hat itself, obviously. And you cannot write directly x as a function of x hat, because this is what your system is giving you. This is part of the plan. You cannot rewrite it somehow magically to something else. This will not work, right? And then you have b times some input, and in your case, input is r now, input of the closed loop system with that observer in the loop. So this seems to be like, it's not supposed to work at all, because you have interdependencies of all of these pieces somehow together, right? They all dependent on each other in multiple different ways. All of the inputs and x's and like all of them are mixed in all of this equation. So both in that equation for the plant, you have x hat and x, and in also like estimated x, you have both x hat and x on that side. So you cannot get rid of that anyhow, but you can. And this is what separation principle is saying, that you actually can. So you can find realization of that system in state space. And this is a little bit tricky. You need to find some particular similarity transform for that. That will completely separate observer and controller, and they will be decoupled completely in that realization. And as you remember, similarity transform is not changing transfer function, it's not changing any other properties of the system. It's still the same system, which is different realization of the same ordinary differential equation, practically speaking. Just you have many of them, so you can choose. So we will choose one specific one, which is a very interesting one. So I'm just copying these equations again. So I have x dot and x hat dot. I'm copying these results here for your convenience. Okay, you will not need to switch between these two slides. Okay. So that a little bit. I can write that as block matrix, and this will look like a linear system now, but of order 2n by 2n. Okay, I'm practically putting those two vectors together as a single long vector of size 2n by 1. All right, so I'm taking both of these vectors together as one long vector, like one order n, another order n. Is it clear so far? I'm taking that longer. And now I want to write that as some matrix times that vector plus some other matrix times input r equals dot of the same matrix. This is my linear system representation in general. Obviously, the system is double order, as twice as big as the original one. So you need 4 blocks, and each block will be of the particular size that will match the dimensions. This is how it's supposed to work, right? So here are the blocks. I'm just copying these equations. Pay attention that I'm just using these equations. So x dot equals ax. So this is block of a times x minus bk times x hat. It's minus bk times x hat. All right. Plus b times r. So it's plus b block times r. Pay attention that all of them are blocks. Okay, these are 4 blocks. These are 2 blocks, 2 blocks, and 2 blocks. Okay. So when you multiply block matrices, you multiply them as regular elements of the matrix. It's like block times that block times that block, if the dimensions connect them together well. Okay, if you have the right dimensions of the blocks. And here you have them right, because all of them are n by n, practically speaking. All of this matrix is n by n, vector is n by 1, so it's like 2n by 1. So all of the dimensions match. So this is first equation. Second equation, you have LC times x This is that part. And Z matrix times X hat plus B times R. This is what you have. So this is a regular linear equation of 2n order, right? Pretty simple. Still not getting me far, right? It's like, it's still not separable. You do not see any separation in here. So let's try to transform that matrix somehow. And this is the trick. I offer you some particular similarity transform, and this is obviously invertible matrix, but more than that, the matrix equals to inverse of itself. So if you multiply that matrix by that same matrix, you get practically matrix I, which is like matrix is the inverse of itself. Very nice property, very convenient. You don't need to invert it. And here's how I'll define it. So what this matrix is doing, it's keeping the first element, which is that vector x, as is, and replacing the vector x estimated with the error, which is x tilde. That's what it does, because what it does is like taking the first element, which is x, minus the second element, which is x estimated. So x minus x estimated is x tilde. This is the error. So practically, I'm converting the dynamics of the system from dynamics of the estimated state to dynamics of the error of the estimated state. Okay, this is what the transform is doing. Just trying to explain the intuition behind it. You don't need that intuition for anything. It's just like this is what it does. Okay, it keeps the first block as is, and second block replaces with x tilde. Okay, as we defined it before. So this is the connection. So x, yes.
I forgot what X tilde was.
X tilde is x minus x estimated.
Oh, okay.
This is the difference. This is the error. That part. What was that? This x tilde.
Yeah.
Estimation error. Okay, so let's see what happens if we transform it that way. So you get from z vector to z vector. And pay attention that this inverse is the same as the original matrix. So it doesn't matter if I write here inverse, same matrix. So let's write x dot and x tilde dot now. Because if you remember in open loop, without connecting the x estimated to the k, we had that just converting to zero, right? All of the exponents needed to convert to zero based on the A minus LC matrix. Everything was nice, but now it's connected to K and other things, so it could modify the observer itself somehow, maybe, but not really. And here's why. So I'm writing these equations for error, how the error is changing in time, and this is how the actual state is changing in time, given that you have estimator in the loop. And let's see how it works. So this is T inverse and T on that side. Remember, similarity transform is T inverse AT. This is how you convert from one representation to another, okay? And this is that original matrix that I'm talking about of your system in closed loop. This is your closed loop system with observer. Times that new vector x and x tilde, which is the same vector without dot. Now, matrix B, similarity transform is T inverse B, the original B. So my original B is that vector. So it's T inverse B times R. This is what the thing is. All right, so far, or too fast. Okay. But pay attention that if you are actually doing that algebraically, like you're multiplying by Z block matrix, and again, it's like block by block and all of the regular manipulations, multiplying that by the same matrix on that side, this is the matrix that you will get. This is your new matrix, all right? And this is a matrix that you will get from multiplication of T inverse by Z matrix. Again, these are blocks, B block, zero block. Here is like n by n zero block, n by n matrix, n by n matrix, n by n matrix, right? All of them are matrices. So this is my new system after that transform. And this system is supposed to have exactly the same eigenvalues in closed loop and transfer function in closed loop as this original system, all right? Because this is just similarity transform that I made here. But pay attention to what happens here. That's very interesting. Now this is block triangular matrix. And if you remember, eigenvalues of block triangular matrix is sitting on the main blocks of the main diagonal. So you don't care what happens actually to that part and that part, okay, in terms of stability and other properties. And pay attention to how this equation look like. So this is x tilde dot equals a minus LC in parentheses times x tilde plus 0. This is exactly the same equation as it was in open loop. So addition of controller, like I added now controller, closed loop, it's not even there. The error is decaying to 0 exactly the same way with controller or without controller in open loop and closed loop. Doesn't matter what UK is, it's not even in the equation, right? It's not participating anywhere in here, right? Pay attention to the first equation, how the state works. You don't have anything with L here at all, all right? It's not connected to L in any way, right? It's still that matrix A minus BK, and like you do not have anything with L at all. So L disappeared from the equation, which means that controller design will not really dependent on like what L you designed and what you did with your L state. You can design it completely independently. And let's see what happens to transfer function, okay? In closed loop, this closed loop transfer function. If you remember, closed loop transfer function is matrix C times Si minus A plus Bk inverse times B. You have also plus D, but I'm ignoring the D part, right? So this is regular closed loop transfer function for D equals to 0. Now I have all of these new matrices like Z, okay, or Z. These are my new matrices. They are like bigger matrices, 2n size matrices. And my claim is the transfer function will not even change, even with this like twice bigger matrices. Here's why. Let's try all the tilde matrices, and tilde matrices are these bigger matrices, okay? Tilde matrices. And again, transfer function using this matrix will be exactly the same as using this matrices because they are similar, right? Similarity transform. And we prove that for any similarity transform that you would choose, and in particular for that similarity transform, transfer functions will not change. So it's easier just to work with Z representation instead of Z representation, but you will get exactly the same transfer function. Okay, so it's C tilde times Si minus A tilde plus B tilde K inverse times B tilde. So I'm writing that explicitly, all of this like big block matrices. And this is triangular matrix, so you have formula to invert in triangular, block triangular matrices, okay? That will be Z inverse, and something else here. And we don't even care what's that something else here. Because, I mean, you can use formula, you can compute it, but you don't care because it will cancel out. And this is B and 0, so it's this part, okay, B and 0. So here is how it looks like. So it's C0 times this inverse block, and something here, whatever. And you have formula for that, but I don't even want to compute it, right? You'll have something here. Multiplying by B0, why I don't care what is here, because 0 is here. So this something will be multiplied by 0 anyways. So it will be Z thing times B plus something times 0 for the first line, and 0 times B plus Z thing times 0. This will be the second thing. And all that is multiplied by C0 on that side. And now I have C times that thing plus 0 times 0. So I get that thing, C times that thing, which is what I wanted it to be, right? So your closed loop transfer function is not changing with adding controllers, not controllers, observers to the loop at all. So they are completely independent, no connection. You design one separately, another separately. You want them to be in different, having different poles for each one of them. That's fine. Choose them wherever you want. They will not affect each other at all. Any questions? And I understand that like first time you see it, probably it doesn't look like magic, but it is. First time it's like, oh, another math stuff, right? With that, interesting fonts on that computer, I would say. Well, we have matrix A, which looks like probably Scandinavian language. And the original matrix was supposed to be, let's see, what it was supposed to be. Zero, one, one, zero. The A matrix. Okay. And the B matrix was C matrix was 0 minus 1. Okay. That's what it was supposed to be. Yes,
I got it.
sure. Okay. So you want for that system, and C matrix is 1, 0, D matrix is 0. You want to check controllability and observability of the system first to make sure that you actually can design controller and observer. So pay attention that observer you can design in that case if the system is observable. Okay, we discussed it in one of the previous lectures, but this is a condition. If the system is not observable, sometimes you still can design observer, but you'll have the same issue as with controllers, which means if the pole which was canceled for the non-observable pole is stable, it still will converge, but you cannot control how fast it will converge because you will not be able to move it from its place. Okay, so it will converge as fast as it can based on its location in open loop, right? But other cases, you can control all of the locations of all of the poles for the controller. So let's build controllability matrix, which is vector B and vector AB. So if you multiply that interesting matrix by that vector, you get -1 and 0. So this is obviously invertible matrix, so it's full rank. Rank is 2, and the system is controllable. Same thing for observability, you're getting 1, 0 as a first row, and second row will be multiplied by A, so it will be 0, 1. You're multiplying that by that thing, this matrix A. Okay, and then you'll get that matrix, which is also invertible. This is I matrix, and it is observable, right? And now you want to design controller with poles at particular place, and you want to design observer with the poles twice as fast. So they are 2 times the location of that thing. And pay attention that I care only about technically that location, like -1/2 versus -1, because this is the real part, like how far away they are to the left. This is what decides on the settling time, how fast they converge. Okay, so we are designing controller poles at -1/2 plus minus 1/2 j. So the desired polynomial is that polynomial S minus that first pole, S minus the second pole, and they obviously conjugate poles, right? You have to have them. And this is your desired characteristic polynomial in closed loop. This is what you want to have your polynomial in closed loop. AK, which is comparison of coefficients, is determined as I minus A plus BK, same formula. Hopefully soon enough you'll learn it by heart for your homeworks. And then A minus BK is that thing. So you're subtracting as I minus that thing, you get that determinant. And then the polynomial will look like that. You can compare coefficients. Minus K2 will be equal to 1, which is coefficient of S. And minus K1 plus 1 will be equal to 0.5. So you have a system of 2 equations, solve them, and you get ZK. Okay, done with the controller design. And what I propose to you before you start homework, okay, before you solve any questions for the homework, try lecture problems, close the solution, try to solve it by yourself, by hand, to repeat that solution before you look at the solution, because typical problems that people are having, they just looking at the solutions, they're saying, oh, looks familiar to me, like I know how to do it, right? It's like, I will not waste my time on that, kind of doing that by hand and trying to replicate the result. And then you are missing some important step somewhere, okay, because you haven't got it, or you missed something, or for whatever reason, you're just missing something important. And then when you're solving homework or test or whatever on the topic, you just don't know where you failed, because you're kind of thinking that you're repeating the same steps, but you're not. Okay, so I'm trying to give you relatively simple examples, which you can like not spending like half a day solving this exercises. Okay, that's not the purpose. Where you can go and replicate the results because you have solution for that. Okay, but try to replicate without looking at the solution and then compare to the solution and see if you got it right. This is the best way to learn it. Okay, you just need to do it once on one exercise, just to make sure that you understand the principles, you understand the process. Then you can repeat exactly the same process on other exercises. Okay, you can kind of gain some experience with that. Okay, and this is the observer design, which is practically exactly the same. All right. So this is your new location, and alpha tilde will be S minus the first location, S minus the second location. This is your desired polynomial for the observer, okay? To which we will compare coefficients. And then this one, I'm replacing BK with LC. And again, L will be L1, L2. You can compute that matrix. This matrix will look like that. Determinant of that matrix will be that element times that element minus that element times that element. You'll get another polynomial as a function of coefficients L. Comparing coefficients L, so L1 is very simple, it will be just 2, right? Because we're comparing 2 to that coefficient. And minus 1 plus L2 will be also 2. So L2 will be 3. So you have observer vector 2 and 3. Done with observer design. Okay? Any questions? And again, you can use Pasgura formula, use Ackermann's formula, all of the above. And here's how it looks like, really, that type of output of the system, just to compare how with or without observer you can get different results. So this is that system in particular. And first system is open loop response to particular initial conditions, which are probably like minus 0.6 and 0.5 for two different states. So I'm starting with 2 different points. And they obviously diverge because the system is not stable. That particular system is not stable. And they will just diverge to minus infinity eventually, okay, in open loop. This is the states as they go in time, and they kind of get lower and lower and lower. Now, in closed loop with controller where you have access to the state X of the original system, this is how X's will converge. So I'm designing location of the poles at negative 1/2 plus minus 1/2 J, right? And then connect to the original state X. And I get that type of convergence. So converging probably like about like 3 seconds or so. Okay. After 3 seconds, it's more or less converged to 0 from initial condition 0.5 with 0 input. Okay, this is convergence from initial conditions. Now I'm adding observer in the loop. And pay attention that here I have access to all of the X's, to all of the original X's, but typically I don't. So I need to design observer for that. And when I'm adding observer, what happens is now you have 4 values. Observer, both values start at 0 initial conditions, okay? So these are that like cyan and red. These are observer estimated states. And these are the original states. So pay attention that they are starting from different points, right? So this is like here, they start from 0.5 and negative 0.6 or whatever, okay? And my observer starts from different states. And this is estimated states, and these are real states, okay, how they change in time. Pay attention that this is converging much farther in time than would be converging if I would have access to all of the states, but I don't. So now I don't have choice, really, but to design observer. And what happens is, eventually, red one converges to the blue one, right? And cyan one, which is estimated, converges to the green one. So the estimated states, after about probably 2.5 seconds, converge to the actual states. And from now on, I actually can control, and this is why it takes a little bit of transient time to start controlling it in a better way. But it's still promised to converge, okay? It's not diverging. It's still promised to be stable because you're not affecting stability by introducing your observer into the system. It always will converge, which is, and yeah, you'll have maybe higher oscillation a little bit and slower convergence, but they will converge, and eventually, like after probably like 7 seconds, it converges to the 0 states that you wanted, all of them to converge. Okay, so this is closed loop with observer. Any questions on that? And this is AI picture how it thinks about our course. Modern control theory. Pay attention to the pronunciation of AI. So it like does really great at getting good pictures, like nice looking pictures, even realistic pictures if you want to. It's really horrible at text. I don't know why. Why it's using like text in the pictures, which is not even correct syntactically. This is interesting. All right. Any questions? Thank you.